Let's start by fixing some y in the interval 0 infinity. For this value of y, define a function f which is in C2 by, I'm claiming that it's in C2 before I define it, which is always a risk, but defined by ux minus xy, which is clearly in C2 because u is. Differentiating f gives that f dash x is equal to u dash x minus y. And if we set this equal to 0, we have that that's equivalent to u dash x being equal to y. Nothing fancy going on there. Differentiating once more gives that f double dash x is equal to u double dash x, which is greater than 0 by assumption. This will all be useful in a moment. The fact that u is strictly concave implies that the derivative of u is strictly increasing. And thus it's bijective, since it's also continuous. And so has an inverse. U dash minus 1, which we shall denote by the letter I, because writing u dash minus 1 all the time is a nightmare. Since u itself is strictly increasing and strictly convex, it has a global maximum, and therefore so does f. So better, since u strictly got the word maximum wrong. Global maximum at this value, which we just calculated, u dash x. No, sorry, at, not u dash x, at x such that u dash x is equal to y, which, since u dash has now, as we know, an inverse, we could write as x, wait, what am I writing? Oops. X equals I of y, taking the inverse of both sides. Recall this y is fixed, right? We fixed one y at the start, and this is all for this fixed value of y. So f, our function which depends on y, has a single global maximum at this value, this input value of x. Therefore, for any y in 0 infinity, we've shown that v of y, which is defined as the supremum over all x's from 0 to infinity of ux minus xy, this is of course our function f, is equal to the value of that function at its maximum, which is uiy minus iy multiplied by y. Of course, it's not necessary by definition that v attains like a maximum, but we know that it does. In this case. Now we can show that V is C2 and itself also strictly convex. Differentiating V gives V dash just using the chain rule, differentiating the outside with respect to the inside multiplied by that of the inside, minus and then the product rule. And now you can see why we use the notation of I, because otherwise these dashes would be getting confusing. Now u dash of IY is by definition equal to Y because they're inverses of one another. So this on the left hand side and this on the right hand side cancel, and we are left with just minus IY. And differentiating once more, gives V dash dash Y equal to minus I dash Y. Now with a little bit of magic, connecting this to U, what we have of course by definition is that U dash of I of Y is equal to Y. We can differentiate that to see that I dash Y multiplied by U dash dash I of Y is equal to 1, and therefore that I dash Y is equal to 1 over U dash dash IY. So V dash dash Y is equal to 1 over U dash dash I of Y. The reason for this, you might be wondering why on earth we do this, is because we know that U dash dash is positive. So this is greater or equal to 0, and therefore V dash dash is also positive. Sorry, U dash dash is negative. That was close. So V dash dash is positive. Thus, V is, and of course, because U is C2, and V dash dash is just given by a continuous transformation of U dash dash, we have that V is also C2. So V is a C2 function. V is strictly decreasing. That's because I is positive as the inverse of U dash, which is strictly increasing and positive. I is also positive, so V dash is negative from this equality. So V is strictly decreasing, and since V dash dash is greater than 0, V is strictly convex. In part B, we can use the fact that V dash of Y, as we just showed, is equal to minus IY, to directly see that the limit as Y tends to 0 of V dash Y is equal to minus infinity, because I has limit infinity. Because U dash has limit 0, so I will have limit infinity, so V dash Y will have limit minus infinity, since U dash tends to 0. And in a similar, well, just in exactly the same logic, V dash Y goes to 0, since U dash tends to infinity, as Y tends to infinity. Now, finally, looking at a very specific example, let Ux equal log x, which implies, as we well know, that U dash is equal to 1 over x, and therefore that I of y is equal to 1 over y, because the inverse of the reciprocal is again reciprocal. And thus that v of y, which this is something we calculated way back in part A, is equal to uiy minus iy times y, is equal to minus log of y, that's the power of minus 1 coming out, minus 1. Then we calculate the derivative of v as minus 1 over y, and therefore vy plus xy has a global minimum at point 1 over x. That's just plugging in v dash y, differentiating xy with respect to y, and setting equal to 0, the classic way of finding the maxima or minima. Therefore, v star, which is defined to be the infimum over the positive real line of this function, which we just found the minimum of, is equal to the value of that function at that minimum. Putting in 1 over x. So minus log y becomes log x, minus 1 is of course unchanged, and plus xy becomes plus x over x. We get cancellation of the minus 1 and the x over x to get just equal to log x. So in this case, v star has come full circle and is just equal to u again.